Okay? All right. So the rest is just a basic calculation. I can just, I don't know if you do this, but I do it. If we have so many point loads, it's getting closer to uniform load. So I don't use the calculation from point load. I just use WL square over 8, just like that, to approximate the moment. And then when I have the moment, I can turn this into the force in the top and bottom chord by dividing it with the moment arm. Right? And for the maximum force in the diagonal web should be the one closest to the support, right? So I can just take the reaction and divide it by the sine theta to get the force in the diagonal member right away. That's pretty simple. Again, if you think you want to know more, if you think I go too quickly, you just put a break on me. Okay? And again, like I said, I got the moment equal to 17.5 ton meter. So I convert that into the proper unit, multiply by 1,000 into kilogram, multiply by 100 to change that into a centimeter unit. And I divide by the moment arm. And to get the area, remember, our formula is the area multiplied by F critical, right? That gives you a force. And the thing is, we don't know F critical because we don't have the section yet. So I approximate the F critical over factor of safety. Let's say it's 1,000. By doing this, I can have the cross section, say the preliminary design of the cross section area. And from this, I can start picking my members. But, ladies and gentlemen, the first example, I want to use the pipe. And the pipe is not made of SS400 steel. It's made of the I don't remember the name, but it's a different grade. So FY is 2400, not 25. It's slightly different. But if you use 2500 all along, it's just like 5%, right? We're not going to die from it. But you may not sleep very well, that's all. Knowing, I've done it wrong. But yeah, that's fine. But the point about using the pipe section is just because some of my students, my former students, just asked me about this. And yeah, I have to tell you guys that yesterday there's a big guy, a big engineer from Germany. He came in and gave the talk about the pipe section and the tube section. It's the most efficient cross section that you could use, right? The pipe, the square, because the moment of inertia the same on every axis. So you don't have neither the strong axis or weak axis. It's good, right? And because the general mass of the cross section is far away from the centroid, and yet you have a symmetric section. So it is very, very, very efficient, at least for compression member. And you see how easy that is? 1R, right? Cool. We just go ahead and calculate it. But before that, let's check that we don't have the issue with local buckling. That means our section, the wall of the tube is not too thin. And of course, D over T ratio is 20, which is much less than the limiting ratio. So we don't have a local buckling problem. And we have already considered the unbraced length of the T1, as I said. We have the purlins coming in every 1 meter, and we have the panel every 1 meter. So we have the unbraced length equal to 1 meter for both axes. 2 microphones. Stupid. Okay, let's save the energy for one. And yep, according to this, I can just calculate my K over R with K equal to 1 because it's pretty clear that it's pin, right? So I have the K over R, which is less than my limiting limit, because it's 137 now, more than Fy equal to 2500 a little bit. So this is less. That means I will have the inelastic buckling. I can just calculate Fe and plug it in this formula. Simple as that. And there we go. We have this. Divided by factor of safety, I have design strength. end of compression member as we know it. Okay, and this is AISC 89. Woo! Pretty much the same. Compared to this. 35.5, 36. Right? Should be okay. So it's just to demonstrate that they're just two different formulas that have the same purpose, that is to approximate the compressive strength of our member. So it's your choice. You can use either one of them, the one that you are most comfortable with. Okay? Any question, ladies and gentlemen? It was such a pain for me, you know, almost 30 years ago. Right. I studied this in 1993, maybe? Very long time ago, yeah. So it's the same. So now for tension, let me just skip that. It's too easy. And again, we have the compression member. I think this is for the vertical web. Okay, so it's just the same calculation. Let's just skip it. Okay. Now we have the calculation on T2, I suppose. And now this time I'm going to have to use some calculation based on the real behavior. So I have, that's a formula for bending moment, right? Because I think it's coming from this. But it should not be a big problem to you. We have that, right? Whatever that is. So I just calculate the maximum moment at midspan. Okay? If that's a P, that's 1.5 P, right? So moment at midspan is going to be 1.5 P multiplied by L over 2, and then minus P multiplied by L over 4, something like that, right? Come on, this is basic structural analysis, right? Okay, so you have a question on that? Perhaps not? Excuse me. So again, I have the moment, and I use the same approximation to get the required area for my prelim design. This time, just to demonstrate a point, I use the H shape. So, you know, you should know that a square section like this is for compression member, right? So I picked the H 250 by 250. Now we have two different radii of gyration. That's a plural for radius. A plural becomes a radii, and it's R-A-D-I-I. That's plural form. And we have that. And then now we need to consider both axes. And before that, we need to check the local buckling. So I check my flange with this. You can take this number from the table. And then we check with this limit, 0.56 square root E over Fy. It's fine. My web is also fine. So we don't have the issue with local buckling. We can just go ahead. But remember, this time my unbraced length in the x-axis is 2.5 meters. But in the y, it becomes 5. It's from this, right? Here. Right? The T2 has T1 coming in every 5 meters. So T1 becomes the braces for T2. For the out of plane bending, buckling. And this means that for the in-plane buckling, the unbraced length is 2.5 according to the shape of the truss. Okay, so now when we have this, we need to check both axes. And KL over RX, L is 250, again K is 1. And for why? Because the buckling is pretty much like that, but in some cases they allow you to use K equal to 0.65. So we need to check on that. But this case, it's pretty clear that it's 1. So yeah, we can use 1, and this becomes the governing slenderness ratio, which is 79.5, but still less than this limit. So we can calculate the FE and then F critical the way we do it before. Okay? And this is the true force. Now when I have the true section, I sort of went back and recalculate the couple again by using the dimension of the H250. So the true force is 93.3 tons. So we are okay. And again, this is the comparison with the OASD formula, and it's just pretty much the same number. Okay, and we have more examples, but with the T's and the stuff, I think I'd like to skip that for the time being. Otherwise, we will not be able to go through the flexural members. Okay, and let's see if you can go through this by yourselves tonight, or just maybe in the future, and then we can talk about that. But for now, please excuse me. Let's go to the compression member. I'm sorry, the flexural members. Just pretty more of the same, you know. Okay. It's just the example of how we can do that. Use that. Flexural members, another 80 pages. Okay. Now, I think, I don't know if all of you have the idea of the plastic behavior of the beam. Because when we consider the beam, it's somewhat similar to compression member and somewhat different. Because, first of all, the stress is different. In compression, it's a uniform stress. But for bending stress, it's not uniform because you have both compressive and tensile stress on the section at the same time. So when we have the stress that is not uniform, sometimes they use the word gradient to say it's, you know, because the values vary. So we call it a stress gradient. It's like a big word, you know. What the heck is stress gradient? It's just a stress that changes, okay? Anyway, the general idea is, again, if it's ASD, we use the factor of safety, and if it's LRFD, we use the phi. And we have 2 issues. The first is the local buckling again, because whenever you have compression, the buckling will come after you. So now we need to check the local buckling of the flange and the web, and the buckling of the entire beam. In compression members, we call that flexural buckling, but in the beam, the buckling is called lateral torsional buckling, because when it occurs, your beam will move to the side and twist. That is why they call it lateral torsional buckling. They move sideways and twist at the same time. Okay? But before that, if lateral torsional buckling does not occur, let's say if we can prevent that, what can happen to the beam is that the beam can reach the plastic behavior. Now, before I go into this, I want to know if any of you are clear about plastic behavior so that I don't have to go through this. It's quiet. So that means I better go through it, right? Okay, it's quiet. So let's say this is the strain and this is the stress. This is the first U. If this is the stress-strain relationship, the true stress strain relationship has a curve here, but we modify it because we want just the good approximation, right? We don't need exact solution. So that means I can just say, okay, I use two straight lines here. But that also means when I reach Fy, I can continue to have Fy, and the stress will not increase while we can increase the strain. So that means when I have the first yield, gotta get up. Okay. When I have the first yield, right here, this is the elastic stress, the yield stress, and this is the yield strain. But when I continue to add more moment to the section, what will happen? The strain will go beyond the yield strain, but the stress will not, because this is our stress-strain relationship, right? So no matter how much you increase the strain, the stress will remain at yield. But the strain will keep going and going, and what will happen is that this is where the yield strain is. So this is where the yield stress is. But the point above this cannot go beyond the yield stress. It keeps yielding and coming down until I reach the point where the strain is supposedly reaches the infinity. So that is the point where we have yield for the entire section. So look at the stress diagram here. It's yield stress throughout. And this is when your section can no longer carry any more moment, because it just yield for the entire section. So when it yields entirely like this, at that particular point, the plastic hinge is formed. So it is ready to go down because you just add another hinge to a beam, right? So when I draw the picture of a beam, you will have something that looks like this. Pink looks beautiful. This is already a hinge, right? This is a perfectly stable structure. If I have a point load here and I keep increasing it, and that situation occurs where the stress is Fy for the entire section. So that means this becomes another hinge. And your beam is so ready to go down like that. And the internal strength of that beam at that particular point where your stress is like this, this is called plastic moment, or MP. And this is the basic use of the steel structure. And we can always reach MP when we brace our beam properly, so that it doesn't have buckling problem. When your beam doesn't buckle, it will reach MP and will be totally, absolutely destroyed, because it's going to have a plastic hinge somewhere. Okay? So, okay. Oops, forget this. So, for the elastic behavior, we will calculate the stress by using my over I formula, right? You know, it's very hard to believe that it takes a human being quite a long time to be sure that this formula works. They got to use some sort of a continuum mechanics to prove that by the guy named Bernoulli. Bernoulli, but not Euler. It's Bernoulli. Bernoulli, they call it perhaps Euler too. I think it's just the name of Bernoulli Euler beam, yeah. a crazy beam to show you that, hey, stress is equal to this. You can be very confident in its formula, things like that. And in general, in steel structure, because this distance is constant, and this is the section property, so we convert the d over to the I divided d over 2 into the value we call the elastic section modulus, or S. Okay? And likewise in the y-axis. So this is the first yield. The elastic section modulus multiplied by Fy, because I can just move this multiplied by the stress, and if the stress becomes Fy, then this should give you the first yield moment. Okay? Now, ladies and gentlemen, you should know that if you look at the steel table, you don't see S, because the steel table in the market is created based on Thai industrial standard, TIS, or more, right? But somehow they created that by, looking at the Japanese industrial standard. And Japanese, because I don't know, it just came to me that because they cannot pronounce Z, so, or they cannot pronounce an S, right? It's the way the language is. So they call the elastic section modulus with the Z. I don't think the Japanese can pronounce S. And they love to switch between M and N as well, right? And L and R somehow. So because of that, and because TIS is based on JIS, so in the typical steel table in the market, they use Z for S here. Remember that we use this according to AISC. We follow AISC in terms of strength approximation or prediction. But we have a standard that is based on Japan. So Thai engineers are very, very good, right? We can handle everything. Anyway, so, but the tables that Kun Tam has attached for you, it's from me. So you have the true S and the true Z. Keep in mind that if we use AISC to approximate our strength, the S here stands for elastic section modulus. And then you're going to see in the next few slides the plastic section modulus, which is denoted by Z. Okay? And here we are. When it comes to plastic, the equilibrium, the internal equilibrium is different because it is based on this stress distribution. Okay? So to obtain internal equilibrium, you need to set compression equal to tension. That means if your section is made of one material, when I change compression and tension into the stress multiplied by the area, this stress is cancelled out. So to obtain internal equilibrium, it means that the area that carries compression must be equal to the area that carries tension. And if you can find this, it means the axis that separates the area that carries tension and compression will become the plastic neutral axis. Okay? You know the funny thing about the word neutral axis? In Thai, they have the specific word for it, right? For the word neutral axis, which deviates the true meaning of it. What neutral means? Neutral means, it's not positive, not negative, not compression, not tension. So the neutral axis is the axis where stress is zero, yes. Which the Thai word doesn't, give you the true meaning of the axis. Neutral axis is the axis that everything is neutral. The stress is zero and the strain is zero. Correct? If you go back and look at the elastic neutral axis here. Stress 0, strain 0. That's why we call it neutral axis. And that's why we measure everything from neutral axis, because that's where the 0 is. But for plastic, neutral axis is the axis where the equilibrium is, right here. For this, the stress is not 0, the strain is not 0. But just the axis where we have equilibrium, okay? And in terms of that, once we figure this out, we can calculate the internal moment, right? Because it's a resistance against the external moment caused by the load. And the internal moment is again based on this free body diagram, this stress distribution. So we can take moment about the plastic neutral axis, and I have compression multiplied by yz, which is the distance from the plastic neutral axis to the force. And then I have the yt, which is the distance from, again, the axis to tension. And again, I can change this into the area multiplied by the stress. And if we use the same material, I can bring the stress out of the equation. And therefore, I have this term. It becomes just the area under compression multiplied by the moment arm, the distance from the force to the plastic neutral axis. I can just call that moment arm, right? And likewise for tension. And this, ladies and gentlemen, is called plastic section modulus. Okay, so now you know elastic section modulus is based on elastic stress distribution, the triangle one. But the plastic stress distribution is based on the rectangle one, the stress when the plastic hinge is formed. Piece of cake, right? And I can sum it up by calling this plastic section modulus, or Z. Now keep in mind that the true plastic section modulus is this one, and the Z in the steel table available in the market is elastic section modulus. Okay? And the basic definition of the plastic section modulus is that one. And now, again, to sum up our definition, the first yield moment is equal to elastic section modulus multiplied by the yield strength. And the plastic is plastic section modulus multiplied by the yield strength. This is the moment with respect to elastic neutral axis, and MP is the moment with respect to plastic neutral axis. Okay? All right. And one more thing, a little useful thing, we call shape factor. It's the ratio between MP and MY. It's the ratio that can tell you how much moment you have left in the section once you reach the first yield. It's rather useful in one way. And it's the OASD, they use the stress to design the beam, right? So they cannot differentiate between MY and MP because the stress at MY and MP, they are the same. The OASD 89 will account for the plastic design by using the shape factor here and multiply back to FY. So the OASD, you have this. Excuse me. Because they use stress, they use the allowable stress, right? So the OSD, you have Fy. The stress you are allowed to use is Fy divided by factor of safety. And the factor of safety for bending is 5/3. So you can switch the numerator and the denominator. So this becomes 3/5, right? So that comes down to 0.6 Fy. So now you know the meaning of 0.6 Fy. Is the Fy divided by factor of safety. So to account for the plastic behavior of the beam, How can you do it? Because they use stress. So the only way to do it is just to increase the allowable stress by using the shape factor. And the typical shape factor value for an edge is 1.1. So the typical difference between the plastic section modulus and the elastic section modulus. You can say that Z over S is about 1.1 for an edge shape. So what they did was use this and multiply back to the allowable stress. So that is why you have 0.666 Fy. Kind of crazy, right? But yep. So they have known about the plastic behavior all along, but because they use stress to design, so they could not really use the true section property to calculate it. Because at that point, plastic or elastic, the stress remains Fy. Okay? And now, ladies and gentlemen, I don't know why the next slide is coming. Anyway, now it is here. I better start talking about it. Okay. Let's do it this way. Okay. What you're gonna see, all the formulas you're gonna see from now on, again, is exact solution. You know, one day, people say, okay, I have the beam like this. It's a one piece of beam. And then I apply the moment like this. So the question is, how much is this moment that is going to cause my beam to buckle? It's a very simple question, right? What I cannot believe is that they solved this by using calculus. It's crazy. But I still have that calculation somewhere in my office. Better go back and look at it. It's crazy and amazing at the same time. It never ceased to amaze me that, wow, that guy was a genius. But the problem is that when they developed this, the bending moment diagram they use is this one. Pure bending, no shear. So when you have this case, your bending moment diagram looks like this, right? And M, which is equal to M critical. This, ladies and gentlemen, is not the real beam in our world. When we have the real beam, we don't have bending moment diagram like this. Right? For example, even if I have a simple beam like this, put a uniform load on it, my bending moment diagram is like that. Not that. When I have something like this, my moment diagram is like that. Not that. So, to account for the real use in the world, we need to modify the formulas that they have, because it's based on this, and this is the bending moment diagram that will cause the very easy buckling. When your beam has the moment diagram that has a gradient, right? That big word. It has a gradient like this, which means moment is not constant. Your beam becomes harder to buckle because, see, the moment here is coming down to zero. So it should be harder to buckle because right here the moment is maximum throughout the length, but not this and not that. So to use the formulas without taking this into the account is very uneconomical. Right? You're going to end up with a section much bigger than it has to be. And again, we use something to account for this, and that thing is called CB, ladies and gentlemen. So CB is a factor that we use to modify the strength of our beam when our beam does not actually carry the bending that is constant like that. And this is one major issue for Thai engineers, I have to say. Because most of them will not understand what this is about, and they end up using CB equal to 1, which is such a waste of a steel structure. It's a complete waste. I have never been afraid of using it. I designed a 12 meter beam, but I use the unbraced length equal to 6 meters, and I use CB equal to 1.67. And the beams still stand and look very, very beautiful from afar because they don't look big. They look the appropriate size because I use huge CB number and I use a proper unbraced length. And you know, it came from the conference yesterday as well during the seminar session that they invited many prominent engineers and instructor to have a chat about steel structure. And one claimed that he loved the steel structure so much, so he tried to build the structure with steel all the time. And he started his business by trying to build the steel house. And the first one that he had, the beams were so big. And he just said, as an understatement, that maybe the engineer just, he had a goodwill for me, so he used the size, the section, just to make sure that everything was safe, something like that, just to save whom, I don't know, save himself maybe, but not just save the owner, because of this. This is the main problem. Okay, and now let's come back here.